Standard electrode potentials are determined at 1 m concentrations. However, cell potentials are concentration dependent. How can we determine the cell potential if the concentrations are not 1 m? Walter Nernst was a German physical chemist who won the Nobel Prize in 1920. One area of his research was the concentration dependence of galvanic cells. The Nernst equation shown here allows us to calculate cell potential at non-standard conditions. E cell is the cell potential at non-standard conditions. E naught is the cell potential at standard conditions. R is the universal gas constant and T is the temperature in Kelvin. Also, N is the number of electrons transferred in the equation and F is Faraday's constant, 96,487 coulombs per mole. Q is the reaction quotient, or the ratio of products to reactants in terms of their molar concentrations. To calculate Q, the products are put in the numerator and the reactants are in the denominator. Raise each species to a power equal to its coefficient in the balanced equation. Molarities are used for concentrations as indicated by the square brackets. Remember that concentrations of pure solids and liquids are taken as unity. By converting natural logarithm into base 10 log and substituting the value of R, F and T equal to 298, the equation can be reduced as shown here. Let's work through a typical problem involving the Nernst equation. What is the cell voltage of a Daniell cell running with 0.1 molar zinc sulfate and 0.5 molar copper 2 sulfate at 25 degrees Celsius? The balanced net ionic equation is given here. Here's a strategy for solving the problem. First, you need to find E cell at standard conditions using our table of standard electrode potentials. Then, use the Nernst equation. From the half reactions, we see that 2 electrons are transferred in the overall reaction. Therefore, N equals 2. Now, we need to find E naught cell by using the equation shown here. E naught R is the electrode standard potential of a right-handed or reductive electrode and E naught L is the left-handed or oxidative electrode. Now work out the expression of Q, the reaction quotient. Since the concentrations of solids are taken as unity, the reaction quotient Q becomes the concentration of zinc 2 ions over the concentration of copper 2 ions. Then, we can substitute our expression for Q in the Nernst equation as shown here. From here, we can substitute our values for E naught, N, and the ion concentrations into the Nernst equation. The ratio for Q can be simplified as 0.1 divided by 0.5 equals 0.2. Now, it's a matter of simplification of the expression E cell is equal to 1.12 volts. pH meters also work on the principle of the Nernst equation. Here is a typical problem you might encounter. A hydrogen electrode is in contact with the solution with a pH of 9. What is the potential of the electrode? Let's work through this problem together. We'll start by listing what we know. Since we're told the pH is 9, the hydrogen ion concentration is 10 to the power of minus 9 molar. The equation for the hydrogen electrode is H plus 1 electron makes 1/2 hydrogen gas. We'll assume that the pressure of hydrogen is held at 1 atmosphere. From the equation, we see that 1 electron is involved, so N equals 1. By convention, the standard potential is 0 volts. Now we can substitute this information into the Nernst equation. From the equation for the hydrogen electrode, we see that Q equals H2 over H plus. By evaluating the equation, we find that the electrode potential is minus 0.531 volts.